In this video, we're going to look at verifying trig identities. When we talk about a trig identity, in our past video, we described an identity as a statement of equality that's always true. So if we look at this first example, and I'm just going to use it as a point of reference, we have cosine theta over secant theta plus sine theta over cosecant theta equals 1. Well, if I look at the left side and the right side, they clearly do not look the same, but that equal sign tells me that they are the same. So this process of verifying a trig identity is writing a proof. You are proving that the two sides of your equal sign are in fact the same. So our goal when we're verifying is to manipulate one side of the equation to look like the other. So a couple of notes here, and I'll explain a little bit more about these after we've written them down. The first note is that you're always going to write both sides of your identity. Let me rewrite this. In each step, we're going to write both sides of the identity. In other words, you're going to write both sides of the equal sign. You are only going to manipulate one side of the equal sign. Or one side of the identity. Now, this last step, I'm going to start with the word usually. Usually is very subjective. It doesn't mean that it's always this way, but it is a good place to start. So usually, you want to manipulate the side that looks more complex. So these are three things we want to be thinking about as we approach the problems that require us to verify identities. Now, after the previous video, you might have thought, how would I have known to take some of these steps without Kelly telling me to do this? And that's a very valid question. With identities and verifying identities, I like to think of it as a video game. And I'm going to date myself a little bit, but when I was younger, one of the popular video games was Sonic the Hedgehog. And in each level, you had, or in order to move on to the next level, you had to beat the boss at the end of one level. Well, oftentimes I had to play the level over and over again, getting a little bit further each time. And every single time I played the level, I learned new things about playing that level, or I learned new things about how to beat that boss. And these things that I learned, and I'm going to call it a trick, I kind of stored them away. So then when I moved on to further levels, sometimes I would think, well, let me try that thing I did back there that worked, or on this previous level that worked. So with verifying identities, some of them are going to be very intuitive. You're just going to think, I think I should try this, and you'll try it and it works. And that's awesome. As we get into more complex identities, or as you get into more complex identities, which might happen in this class, it might happen in future calculus classes, it might take some trial and error. So try to maintain the fun in it, thinking about it as a game. The nice thing about an identity is you know that you've completed it if you end up with a statement of something is equal to itself. Now, one other comment about verifying trig identities is that this type of problem and how we're going to set it up in this video is really difficult to assess or practice in any online environment. So more than likely, you will see problems similar to what we saw in the last video where you're just going to take a trig expression and manipulate it to look like something else. So we're sort of missing the other side of the identity in that case. But that's simply because, again, the work for going through verifying an identity is sometimes difficult to build or code in an online platform. So just keep that in mind. Again, I'm going to be going through these identities in a very formal process. And especially that first bullet here in each step, writing both sides of the identity, this is setting up a very formal proof. So if you remember from maybe a geometry class you've taken in the past, that was really your first foray in writing proofs, more than likely, but that's how I'm going to be setting this up. So you might see these types of problems illustrated differently or set up differently. But again, I'm coming from a very formal lens here. So we've got cosine theta over secant theta plus sine theta over cosecant theta equals 1. Again, we're going to start by manipulating the side that looks more complex. The left side of this equation definitely looks more complex. So this is the side that I'm going to manipulate, and I'm going to try to make that left side become 1. Cosine theta over secant theta. I'm going to start writing this all in terms of sine and cosine. So cosine theta in the numerator is going to stay the same, but secant theta in the denominator, I'm going to rewrite as 1 over cosine theta. Plus sine theta in the numerator, and I'm going to do the same thing with cosecant theta, rewrite this as 1 over sine theta equals 1. Again, here I am maintaining both sides of that identity in each of my steps. In my first term, cosine theta divided by 1 over cosine theta, I'm going to clear out that complex fraction by multiplying by the reciprocal. So we have cosine theta times the reciprocal of 1 over cosine theta is cosine theta over 1. And I can drop that denominator of 1 now. And I'm going to do the same thing with my next term. Sine theta divided by 1 over sine theta is the same as sine theta times sine theta over 1 equals 1. Again, practicing writing each side of that identity. Cosine theta times cosine theta is cosine squared theta. Sine theta times sine theta is sine squared theta. And my last step, I know that cosine squared theta plus sine squared theta is equal to 1 from that Pythagorean identity. So my very final statement, my very final line in this proof is that 1 is equal to 1. And that's how we know that the original identity is in fact an identity. It's always going to be true. We've manipulated in such a way to show that the left side, that cosine theta over secant theta plus sine theta over cosecant theta, is in fact equal to 1. Our next example, we have the quantity sine theta minus cosine theta squared equals 1 minus 2 sine theta cosine theta. If I think about which side to work with, looking at the right side, 1 minus 2 sine theta cosine theta, I don't really have anything that I can use for that 2 sine theta cosine theta, so I'm not really sure how to change that. So because I'm not sure how to change that or manipulate it, I'm going to work with the left-hand side because I can see that right off the bat, I can do something. I can foil it. Again, thinking back to that idea of a video game, a lot of times we just start doing things because we know we can do them, right? If we get to a point where we're like, we can't move anywhere, we can't move forward, sometimes we have to go back to try to go a different path. So that's what I'm trying to illustrate here, in that I don't want to pick the right side because I don't know what I could do with the right side. I don't know how I could change that. So let's start with the left side and see if I can change that to look like the right side. Sine theta minus cosine theta, that quantity being squared, we're going to FOIL that out. And I'm going to write my binomial twice to help me see that FOIL. sine theta minus cosine theta times sine theta minus cosine theta equals 1 minus 2 sine theta cosine theta. Now that we have our two binomials being multiplied, foiling is a little bit easier to see. Some of you might be really strong with that process of foiling and squaring a binomial, so you might be able to do this in one step, but I always like to show going step by step just to ensure that those skills are there. So our first sine theta times sine theta is sine squared theta. Our outer term is sine theta times negative cosine theta, so minus sine theta cosine theta. Inner is negative cosine theta times sine theta, so another one of those terms, minus sine theta cosine theta. And then our last terms, negative cosine theta times negative cosine theta is positive cosine squared theta equals 1 minus 2 sine theta cosine theta. In my next step, I'm going to do two things because one is algebraic and one is trigonometric. So I'm going to do both of them because I think that the algebraic one is a little more obvious. So the trigonometric substitution I'm going to make is that I've got sine squared theta plus a cosine squared theta. So I could rewrite this or change the order, but I don't necessarily need to. Sine squared theta plus cosine squared theta is 1 by our Pythagorean identity. And then our middle two terms, minus sine theta cosine theta minus sine theta cosine theta, those are like terms. So we can combine them. This is minus 2 sine theta cosine theta, which is equal to the right side 1 minus 2 sine theta cosine theta. In example 3, we have 1 over 1 plus cosine theta minus 1 over 1 minus cosine theta equals negative 2 cotangent theta cosecant theta. Now, depending on how you want to look at this, we've got the left-hand side and the right-hand side. The left-hand side definitely looks a little bit more complicated to me than the right-hand side, so that's the side I'm going to work with. In my experience, there have been times where I started with one side, started moving, and because I keep writing both sides of my inequality, I can tell whether or not I'm getting closer to manipulating one side to look like the other. And sometimes I realize I'm not getting anywhere, and then I just stop and maybe I restart that identity and work with the other side. But we're going to start with this left-hand side, 1 over 1 plus cosine theta minus 1 over 1 minus cosine theta. The first thing I want to do is I've got two fractions being subtracted and it ultimately needs to equal one term. So I want to figure out how to make this one fraction. To do that, I'm going to need to multiply by, or to get a common denominator, excuse me. So our common denominator here is going to be 1 plus cosine theta times 1 minus cosine theta. A very easy common denominator to work with is always just the product of all different denominators. It may not always be the least common denominator. In this case, it is, but it is one that will work to get a common denominator. So I'm going to multiply my first term, the 1 over 1 plus cosine theta, by 1 minus cosine theta over 1 minus cosine theta. I'm going to multiply my second term, the 1 over 1 minus cosine theta, by 1 plus cosine theta over 1 plus cosine theta. And the right side is negative 2 cotangent theta times cosecant theta. Simplifying these products, I have 1 minus cosine theta in the numerator in that first term. And then in the denominator, 1 minus cosine theta times 1 plus cosine theta. We are multiplying two binomials, but these binomials are conjugates. If you recall from an algebra course in the past, when we multiply conjugates, let me be more specific, when we multiply conjugate binomials, that middle term of the FOIL cancel out. So we multiply the first term and then the last terms, and that's going to be our product. So the denominator of 1 minus cosine theta times 1 plus cosine theta is 1 minus cosine squared theta. Now I'm going to subtract and start working on the product of that second term. And I'm going to put this in parentheses because we do want to make sure that that minus ends up getting distributed later. We want to be real careful anytime we deal with subtraction or negatives. And we add appropriate parentheses when they're needed. So we have 1 plus cosine theta times 1 in the numerator, which is 1 plus cosine theta, over, and there's the product of those conjugate binomials. So this is going to be 1 minus cosine squared theta equals -2 cotangent theta cosecant theta. On the left-hand side, now what I'm going to do is distribute that minus sign to that second numerator, and I'm going to start putting them together as one fraction since they both have the denominator of 1 minus cosine squared theta. So I'm just going to write that denominator first, 1 minus cosine squared theta. And in the numerator, we have 1, and we're going to subtract 1, so that's going to go away. And then we have negative cosine theta minus another cosine theta, which is -2 cosine theta. And this is equal to -2 cotangent theta times cosecant theta. Already I can tell that I'm getting closer because I've got that -2 factor. In the denominator, 1 minus cosine squared theta is the same as sine squared theta from the Pythagorean identity. So this is -2 cosine theta divided by sine squared theta equals -2 cotangent theta cosecant theta. And similar to a previous example, we're going to factor out that sine squared so we have both factors of sine theta. So we have -2 cosine theta over sine theta times sine theta. Equals -2 cotangent theta cosecant theta. Cosine over sine theta is cotangent theta. So we have -2 times cotangent of theta. And then if we add an invisible factor of 1 in the numerator, which we can always add a 1 factor, 1 over sine theta is my cosecant theta. So we have -2 cotangent theta cosecant theta is equal to -2 cotangent theta cosecant theta. And we've verified that identity. Cotangent theta over cosecant theta equals cosine theta. This looks really simple. There's not a whole lot of terms here. We definitely want to start with the left-hand side because cosine theta, there's only so many ways we can rewrite cosine theta. And it just so happens that all of these examples we're working with the left-hand side. Don't expect that to be the case always. We want to be mindful about choosing which side we want to manipulate. Cotangent theta, I'm going to rewrite this in terms of sine and cosine. So this is cosine theta over sine theta. And then cosecant theta is 1 over sine theta. Equals cosine theta. So again, here I'm rewriting the terms on the left in terms of sine and cosine. To clear out our complex fraction, we're going to multiply by the reciprocal of the denominator. So cosine theta over sine theta times sine theta over 1. Our factors of sine theta in the numerator and the denominator simplify to 1. So we're just left with cosine theta over 1 or cosine theta. Cotangent x plus tangent x equals secant x plus cosecant x. I do like this example because just be mindful we have changed the variable that we're being used or that we're using in this problem. Please make sure that you are conscientious of that. Unless you formally identify that we're going to replace x with theta by using some sort of statement of substitution, you should not be changing those variables. This is a really common issue when students are entering answers into online platforms. If they change that variable, the program is going to think that the answer is wrong. So just be mindful of that and be consistent with the variable that's presented in the problem. And that even includes capitalization. Cotangent theta plus tangent, see, I just did it. Cotangent x plus tangent x equals secant x times cosecant x. We're going to start with the left-hand side and see if we can't work with that. Oftentimes, if I've got two sides of an identity, one has addition, subtraction, the other has multiplication, division, I try to start with manipulating the side with addition or subtraction. I find that that's usually a little bit more straightforward, but again, not always the case. Rewriting cotangent theta and tangent theta, cotangent x and tangent x. Ooh, I am practicing following my own advice here. I'm going to rewrite these in terms of sine and cosine. Cotangent x is cosine x over sine x. Tangent x is sine of x over cosine of x equals secant x times cosecant x. On the left-hand side, we're going to get a common denominator. So I'm going to multiply my first term by cosine x over cosine x. And my second term by sine of x over sine of x. This gives me cosine squared x over cosine x sine x plus sine squared x over cosine x sine of x equals secant x times cosecant x. Combining my two fractions, we have cosine squared x plus sine squared x over cosine x sine x equals secant x times cosecant x. Cosine squared x plus sine squared x is 1 from our Pythagorean identity. So we have 1 over cosine x times sine x equals secant x times cosecant x. Now, the 1 in my numerator on the left-hand side, I can multiply this by another 1 just to see that I've got two fractions. 1 over cosine x is secant x. 1 over sine x is cosecant x. And our last identity, sine squared theta over cosine theta is equal to secant theta minus cosine theta. The comment I made in that previous example, I usually try to start working with the side that has either addition or subtraction over the side that's multiplication and division. So I'm going to work with the right-hand side in this case. So keeping the left-hand side, sine squared theta over cosine theta equals secant theta is going to be 1 over cosine theta minus cosine theta. I'm going to work to get a common denominator on the right-hand side. So I'm going to multiply by cosine theta over cosine theta. So sine squared theta over cosine theta is equal to 1 over cosine theta minus cosine squared theta over cosine theta. Now I'm going to combine my two fractions since they have the same denominator, 1 minus cosine squared theta over cosine theta. And hopefully we're starting to see the light at the end of the tunnel. One minus cosine squared theta is sine squared theta from our Pythagorean identity over cosine theta.